Hello, everybody. Welcome back to class. It sounds like we'll have a special guest, my neighbor's dog, as part of our class today. So if you hear some barking, that's okay. You know, just croissants and a sip. So who's here? Everybody say hi. Here. Navik is here with his coffee and croissant. Good morning, Cal. I'm sure, I don't even know if can you guys hear the dog on the other side? Of course, now he stops, but. Good morning, Emma. All right, Cal can't hear the dogs. All right, so good. Maybe it's just me. It's like the treadmill from the first week of class. Good morning, Shutong. All right, we'll get started in about a minute or so, maybe a little less. Good morning, Taylor. Good to see you. All right, well, it's 9 o'clock. We could get started. So if you would like to join in on this Wednesday edition of the Simultaneous Sip, we could do so now. Good stuff. All right, you know the drill. Let me know if you did the Simultaneous Sip. Oh, we got a couple of new people here today. Good morning, everybody. And love your channel. Well, thank you. All right, so the plan for today, is we're going to finish up 6.1. Oh, Emma had the family sip today. Great. Taylor sip. Navik had a full breakfast, it seems like. Excellent. That's the beauty of the online classes. You could have a croissant during class, and it's not going to be a distraction. Okay, so we're going to finish up 6.1. That should only take a few minutes, and then we'll move on to 6.2. But 6.2 is just like a continuation of 6.1. Okay. Marker is dying. So the definition, if a vector z, okay, so here we have some vector z, and we'll sketch a picture of what this definition is going to be. So if a vector z is orthogonal, remember what orthogonal meant? It means perpendicular, or that two vectors are orthogonal if their dot product is 0. So if a vector z is orthogonal to every vector in a subspace, W, let's say of Rn, then we say that Z is orthogonal to the entire subspace. Okay, so if it's orthogonal to every vector, it's just orthogonal to the subspace. And the set of all vectors that are orthogonal to W is called the orthogonal complement of W. Okay, so the set of all vectors, so it's some collection of vectors where all of them are orthogonal to W. We call this the orthogonal complement of W. And what we write W perpendicular. Okay, so we use this like upside down capital T to denote the orthogonal complement. Okay, so let's take a look at an example. And so we'll look at an example, but just to give you some context, for those of you who have taken Calc 3 or are currently taking Calc 3, think of like the normal lines of the plane. That would be W perpendicular, or the orthogonal complement. Okay, so that's going to be the example we're going to draw out. So example, if W is a plane in R3 through the origin, then W perpendicular, or the orthogonal complement of W, is the line through the origin perpendicular to every vector in W. Okay, so what does this look like in a drawing? Okay, so let's say that this plane here is W. And let's say this is the origin. So here we have just some plane in R3. I mean, it's tough to draw because I'm drawing on a board and then being recorded from a camera. So it's like extra hard to get depth. But so we have, let's say this is some plane in R3. Picture it as a piece of paper here. It contains the origin. This is the subspace of R3. And so W perpendicular is the line through the origin that's perpendicular to the plane. Okay? So any vector on this plane would lie in W. Any vector on the line would lie in W perpendicular. The orthogonal complement to W. Okay, and again, ask any questions you have along the way, um, and I'll answer them when I see them. So the theorem is if W is a subspace in Rn, okay, so we have some subspace of Rn. We could picture this plane in R3. Well, then, so is W perp. Okay, so what does this theorem say? It says that W perp lives in Rn, and it's also a subspace. So it has all the properties of a subspace, meaning it contains the zero vector. It is closed under scalar multiplication and closed under addition, vector addition. But the important part of this theorem, or the second part, I guess, in fact, W is equal to W perp perp. So the orthogonal complement of W is W perpendicular, and the orthogonal complement of W perpendicular is W. So they're orthogonal complements of each other. And this will be useful down the line. Right now, we're just kind of getting some notation, right? Classic first section of a chapter. It's a lot of notation. We'll see more of the applications in a few days. So this isn't just some abstract concept. We've actually seen orthogonal complements in some of the subspaces we've studied this semester. So we'll write that as a theorem. So the theorem says, let A be, well, let's write it there, actually. Okay, so we have some m by n matrix. Okay, and so I'm going to ask for some help to fill in the blanks. So then the first part says the orthogonal complement of the row space is equal to what? What do we call the set of vectors that are orthogonal to the rows of A? That is, if you do the multiplication, multiply down the row and then down the column, you'd get 0. So what do we call the vectors that are, well, basically what it would mean is what vectors, when you multiply by A, gives us the 0 vector? What do we call that set? Does anybody remember? So this right-hand side will be what vectors or what do we call the vectors such that, AX Yeah, good. It's the null space. Right, the null space was the set of vectors that gets sent to 0 by multiplying to A. And you could check if you were to do out matrix multiplication. What is it? We take a row from A and multiply it to the column. Okay, and that's exactly what the dot product is. Okay, and then we could take the transpose of A here, and we'd have just the second part says the column space of A right? The column space of A is the same thing as the row space of A transpose. So the column space of A is equal to null. The perpendicular or orthogonal complement of the column space of A is equal to null of A transpose. Okay, so we have seen orthogonal complements throughout the semester. We just didn't call them that. Right, so the row space of A is the orthogonal complement of null A, and then that just switching A with A transpose would give us this next result. Okay. Are there any questions on anything we've done so far today or yesterday? So I guess before we move on to 6.2, I know this is probably going to make you sad, but we will have a quiz tomorrow, and it's just going to be on the 6.1 stuff. Okay, so I'll send out some practice problems, but the quiz is not going to be difficult. Just make sure you know how to do the dot product and make sure you know how to find the length of a vector, or maybe the distance between two vectors. Okay. The reason why it's tomorrow and not Friday is we don't have class on Friday. Okay. Tomorrow, right? We don't have class on Friday, correct? Am I crazy here? I said that to my calc class. I got the same reaction. Can somebody confirm we have no class on Friday? Okay, and Noah says, "Oh yes." Yeah. So it's gonna be straightforward, and I'll send you some practice problems. But it's just so you can get back in the routine of taking quizzes. No class Friday. Good. Yeah. So just be prepared for a question that's about dot products or length, magnitude type. Yeah, it's going to be literally a good Friday because we have no class. Or the distance between vectors. Okay, so I should just let you know that. So if there's any questions on that stuff right now, we can talk about it. But if not, we can move on to 6.2. So I'll give you a second to ask questions if you have them. Yeah, so the quiz will be the same as the last one in terms of the 8 o'clock people will have time at 8 o'clock or 8:40 to 9:40, and then the 9 o'clock people will have the later time. If you're in the 8 o'clock class and you would prefer to take it later, just email me and we could switch it. I just didn't want it. I know you have time to take the test from 8 to 8, the quiz from 8 to 8:50 because you don't have other classes. That's why I picked that. Okay. Orthogonal sets. So we'll start with the definition and then see an example. So a set of vectors, let's say U1 through UP. In Rn. Is said to be an orthogonal set if each pair of distinct vectors from the set is are orthogonal. So if each pair of distinct vectors from the set is orthogonal. Okay, what does that mean? I.e., ui dotted with uj is equal to 0 if I is not equal to j. Okay, so we'll have some collection of vectors, each of them orthogonal to each other. Again, for those of you that have taken Calc 3 or are currently in Calc 3, you could think of the unit tangent vector, the unit normal vector, and the binormal vector from when you parameterize curves as an example of a orthogonal set, right? Because they were all perpendicular to each other. Did you in Calc 3, do you learn about those vectors? Unit tangent, unit tangent, unit normal, and the binormal? Yeah, okay, good. Yeah, at NC State, we spent quite a bit of time going over those. I wasn't sure about Wake Forest, but I would have been shocked if you didn't. Okay. So let's just work out a quick example. Okay, so we'll show that U1, U2, and U3 is an orthogonal set. Here U1 is equal to 3, 1, 1. U2 is equal to minus 1, 2, 1. And U3 is equal to minus 1 half, minus 2, 7 halves. Okay, so I'll give you a few minutes to work this out. If somebody wants to share in the comments how they plan on doing this question, that'd be great because it'll probably help your classmates. But if not, that's fine. Just give you about a minute or two to try to confirm this. Right, we want to show it's an orthogonal set, meaning each pair of vectors has the property that you take their dot product, you get 0. And after this example, we'll state a theorem and we'll actually do the proof. So get ready for that. It's going to be good stuff. All right, did anybody have any luck showing that this set is an orthogonal set? And if you weren't sure how to do that, that's fine. You'll see that it is going to be pretty straightforward. There's no tricks here. It's just confirmation. Yeah, all the dot products are 0, so it is good. Yeah, so we want to check all pairs of vectors. Okay. So there's three total vectors, and we need to pick pairs of 2. There's 3 ways to do that. We could do U1 dot U2. And when we do that dot product, we have 3 times -1, which is -3, plus 1 times 2, which is 2, plus 1 times 1, which is 1. Which is equal to 0. So let's start by just doing U1 dotted with all the other vectors, and then we'll do U2 dotted with all the other vectors. That's a way to guarantee we hit every vector. So U1 dotted with U3 is equal to minus 3 halves, minus 2, plus 7 halves. Okay, minus 3 halves, minus 4 halves, plus 7 halves is 0. And then the last, we have to check U2 dot U3. We get 1 minus 4, sorry, 1/2 minus 4 plus 7 halves. Well, this is 8 halves minus 4 is 0. Pretty straightforward, right? So to show something's an orthogonal set, you just check each pair of vectors, compute their dot products, and hope we get 0 all the way through. All right, if any one of these was not 0, then we could conclude that it is not an orthogonal set. We need every single dot product to give us 0 when we have distinct vectors. Okay, so thus, now just as a conclusion, thus U1, U2, U3 is an orthogonal set. Okay, so let's state a theorem and then we'll prove it. And this theorem will tell us why we care about orthogonal sets. So if S equals U1, U2, UP, okay, so we have some collection of P vectors. So if this is an orthogonal set of non-zero vectors, okay, so we have a collection of non-zero vectors in Rn such that each of their dot products, evaluate any pairwise dot product, you get 0. The conclusion of the theorem is that S is linearly independent, and hence is a basis for the span of S. Okay, so what does this theorem say? Is if we have an orthogonal set, then it's automatically linearly independent, and so it's a basis for, its own span. It's not a basis for R. It's not a basis for Rn necessarily. It's a basis for whatever subspace span of S is. So it could be lower dimensional, but that's fine. So let's prove this, right? We just have to prove that S is a linearly independent set, and that's the whole That's the whole. That shows it's a basis, right? Because S obviously spans span of S just by definition. So let's prove this. So the question is, we want to show that S is linearly independent. What does it mean for a set to be linearly independent? Not scalar multiples of each other? Yeah, you're on the right track. So that's if you had only two. If you had only two vectors, then they can't be scalar multiples of each other. It only has a trivial solution. Yeah, so let's combine what Cal said and what Taylor says. Basically, we want to express our vector. We'll write out a linear combination of u1 through up, and we're going to set it equal to 0. And we want to show that the weights of each of the vectors has to be 0. Okay, does that sound familiar? Hopefully it does. So so we have a linear, we take a linear combination of our vectors and set it equal to 0. We want to show that each scalar must be 0. Or weight. Right, that's what it means for this equation to have just a trivial solution. It means all the weights are 0. Okay, so the question is, how do we show this? And if you're unsure, just putting question marks or some sort of way to let me know you're paying attention in the chat. That'd be great. So yeah, we have this linear combination adding up to 0. We want to show all the weights are 0. And what are we dealing with? We have an orthogonal set. Okay, so that's likely going to play a part in this proof. I mean, I already know the proof, so I know for a fact it's going to play a part in the proof. But you should, when a theorem is stated and you're asked to prove it, likely they're not going to include unnecessary information in the theorem. Right? Because if they had an unnecessary condition, it just makes the theorem weaker. Okay, so this is probably useful. It's an orthogonal set. So what does it mean to be an orthogonal set? I guess let's answer that question. What does it mean for u1 through up to be an orthogonal set? Yeah, all the dot products equal 0. So let's try to use that to our advantage. And let's just take, so this is, the left-hand side is some linear combination of vectors. The right-hand side is a vector. Let's just take this equation and take, the dot product of it with, u1. So we'll do u1 dotted with the left side should equal u1 dotted with the right side. Okay. Right, so we take the dot product of both sides with u1, and we're going to see that our choice of u1 is not really terribly important. Well, this argument will hold for all subscripts. But yeah, so let's do this. Remember, the dot product has a property that it could be distributed in. So this becomes C1 U1 dotted with itself plus CP UP dotted with U1. I guess we should keep the order right. And then anything dotted with 0 is 0. Okay, and this is a number here, not the vector, right? When you take the dot product, you output a number. Okay, and just for the purpose of clarity, let me rewrite this line and have a second term in there. Just so we can have a few more terms. Okay. And this is a dot product. Can we do anything with this left, or what can we say about this left-hand side that will simplify it a little bit? Right, remember, we have an orthogonal set, which, as we said in the chat, means there's a lot of dot products that go to 0. So what can we say about the right-hand side? Or sorry, what can we say about the left-hand side? Well, U1 dotted with U2, we have an orthogonal set. This is 0. Same with U1 dotted with U3, all the way up to U1 dotted with UP, that's also 0. Yeah, Shutang, so only a U1 would be left. So what we have on the left-hand side, all these terms go to 0. We're left with C1 times, well, U1 dotted with U1 is the magnitude of U1 squared is equal to 0. And recall or note that all of our vectors are non-zero. So U1 is not the 0 vector. So its length is greater than 0. So note. Right, so we have a number times a positive number equals 0. We can conclude that C1 has to be 0. And then a similar argument holds for C2 up through CP. Right, we could repeat this argument and just switch the vector we took the dot product with. And we'd get all of these coefficients are 0. And so since all the weights must be 0, S is linearly independent. And when you finish a proof, you put a box at the end.
let the reader know that you're done. Okay, so again, to recap, and this is a kind of a typical proof technique in a linear algebra class. To get coefficients, you just take the dot product. So orthogonal sets are nice because they turn out to be bases for the subspace that's formed by their span. Okay, please ask any questions you may have. And so we're going to call orthogonal, since an orthogonal set is actually a basis for some subspace, we're going to call them orthogonal bases. So an orthogonal basis for a subspace W in Rn is a basis for W that is also an orthogonal set. And what's nice about orthogonal bases is it's really easy to expand to express a vector, to find the coefficients of a vector when the basis is orthogonal. So let's write out a theorem, and then we could hopefully look at an example. Okay, so we have U1 through UP is some orthogonal basis for a subspace W in Rn. So the theorem says for each Y in W, the weights of the linear combination So let's say we write Y. So Y is some vector in W. We could write it as a linear combination of the basis vectors. So if we have Y is equal to C1 U1 plus CP UP, this theorem tells us how to find C1 through CP without having to do some sort of row operations like we had to do in the past. So the weights are given by the jth weight is equal to Y dotted with U sub j over U sub j dotted with itself. Okay, let me write that again so it's a little easier to read.
but isn't y equal to 0?
No, so this is any vector in W. If we want to write any vector in W as a linear combination of its basis elements, we could do that, right? That's because to be a basis, that means you span the entire subspace. So any vector in W can be written as a linear combination of these. And our theorem tells us, how do we find the weights? Well, we find the weights by performing the dot product of y dotted with u sub j over uj dot uj.
So let's take a look at an example so you can see how we apply this theorem. Okay, so we'll let u1, u2, and u3 be the same vectors as before, as our previous example, and we'll let S equal the set of these three vectors. Okay, so there's two parts. So the first part is explain why S is a basis for R3 and express Y of u1, u2, and u3. Here, Y is the vector 6, 1, negative 8. Okay, and we don't have time to finish this today, so let's just talk about part 1. And then we'll start class tomorrow by doing this part. But I would recommend trying to do this on your own tonight. So explain why S is a basis for R3. Does anybody know why S is a basis for R3? Well, what's it mean to be a basis? We need it to be linearly independent. Oh, good. Yeah, we need it to be linearly independent, and we need it to span R3. Taylor says it is linearly independent because the set is orthogonal. Yes, right. We showed this is an orthogonal set. So S is an orthogonal set. So it is linearly independent. And now, how do we know that it spans R3? Well, we could put this in a matrix and row reduce and see that we get the identity matrix. Another fact we could use is any three linearly independent vectors in R3 is automatically a basis. Right, why is that true? That's true because the dimension of R3 is 3. So we had a theorem that said if you had a dimension n
subspace and you had n linearly independent vectors, it's automatically a basis. Okay, and so we want to express y as a linear combination of u1, u2, and u3. Another way to word this question is to find the s coordinates, right? This is really asking us find the s coordinates of y. Yeah, so we'll use this theorem to do that. We need the dot product of y dot u1 over u1 dot u1, y dot u2 over u dot u2, of u2 dot u2, and so forth. But that's what we'll start with tomorrow. Okay, that seems like a good place to stop in the middle of a question. Remember, hit the like button before you get out of here. That's very important. It's good luck for the test, for the quiz tomorrow. You know, the more like buttons you smash, the better you'll do on the quiz, I'm sure. I'll send an email. I'll send an email later today, just kind of giving you an idea of what you should expect for the quiz. But since you have no time to study, right? You only have one day to study. It's not going to be challenging. Just make sure you're ready, and make sure your technology is ready. PDFs. Let's put PDFs on Canvas. Make it easy. Make it easy for me and the TA. But yeah, so that's all I got. I'll stay around for a minute or so to answer any last minute questions, but yeah, you are welcome, Emma. Yeah, try this question though tonight. And then we'll start with that tomorrow morning. Mia says she likes your shirt today. Yeah, thanks. It's got like a dolphin on it and some fish. I was an aquarium for Halloween one year, and this was my Halloween costume. Okay, well, on that note, bye-bye.